You already I'm going to present you the efficient program exploration by the input fusion. Quick and toward a new approach in the malicious code detection. I'm now currently a PhD student under the supervision of Guillaume Bonfang and Jean-Guy Marion. I come from the Lorraine University. Thank you. And we begin with the context of the problem, and imagine when we examine the bot on the infected host, and we recognize that the bot we do the malicious behavior it and only if it receives some special command from the bot master, and we have a very famous example currently is the Stuxnet and Gauss, and both of them will active if and only if some condition on the infected host are satisfied. And in general, it's called the trigger-based malware because it's malicious behavior if only if it receives some sufficient condition. And for this malware, and we want to study all of its behavior, even when we don't know where is the condition, make it active. And our second purpose and we want to classify, because we want to know how the malware is it reactive when it receives different condition, and then from that we propose a new approach in the program similarity. And for the post proposed, it names the code coverage, and for the support, its research has extensively has many work on this, but it's much fewer when we consider on the binary code and on the obfuscated code. And but why this is so difficult? Because the malware is active when it receives some special input, and then the direct dynamic analysis it doesn't work. And the static analysis it has also many difficult, and because we don't have many work on the binary code, and the most important is because the static is very sensitive to the obfuscation. And then we propose a hybrid approach. For the hybrid approach, we start the program with a concrete input, and we receive a task. And for each conditional branch on this task, we try to find another input, so that when the program is run with input, the program the condition of it depends when we change. And our approach is smart input fusing. The main idea is around the idea of the reverse exclusion with the checkpoint, and the minimizing the number of tests. And it's better when we consider an example. And here we have a program. We see here that it has a 3 conditional branch, and we detect that it have a 3 checkpoint. And for more comprehensive, we have it code the assembly on the right hand. And when we, for example, when we start the program with the method is 47, and the task of program will be here, and we change another input, the task is changed also, and etc. And then here when we receive init when we can detect on the input, and then and then we can explore on the behavior of the program. Now I will introduce our algorithm, and we start the program with a concrete input, and we receive the first test, and we detect the checkpoint, and then we take a rollback to the first checkpoint. Here we try to modify the input. For example, here we try to 67, and then we detect that this input when change the co-decision of the first conditional branch, and then we roll back immediately, and we come back to the first test, and we go to the second conditional branch, and here we roll back to the second checkpoint, and here we try to modify the input, and for example here we try to 49, and then we say that this input can change the decision of the second branch, and then we roll back. And now we see that for the first test we have a result on the conditional branch, and then we come back to the first checkpoint, and we take another input, and we do exactly in the same way. And then with this algorithm we can detect all the behavior possible of the program. For the implementation, for the knife approach is a field testing. Everyone knows that it cannot work because the number of tests is very big, and the cost of re-execute the program is very expensive. And our approach is we use the reverse execution with the, and we try to reduce the number of test input and reduce the size of re-executing test. All of that we use the dynamic testing analysis. The main ideas of the dynamic testing analysis, we construct a program, the data flow program. We use the liveness analysis, and here we can see the propagation from the inputs of the program, and all of that we have implemented in the Pintun, and its code is online, is available online. And here we can test. For example, here I test with the program duplicate. We see here we have here two parameters. The first is the number of rollback. That means we try to restore a conditional branch with this number, and after this number we cannot restore. We bypass it and go to the next branch. The diff here is exactly the diff of the control flow graph of the program, and we'll limit it at the fixed value. And here we have some results. For the wget, we can see that the result ratio we quite stable at 33%, and we see that the detected branch is increased exponentially with the number of rollback used, and we see that the number of detected branch and the number of the rollback used, they have a linear relation. I give you a few work on our ongoing work, where we propose a new approach in the malware detection. The traditional approach in the malware detection compare the similar within no program and an unknown program, and when we see that the tasks have something similar, some for example, some pattern, and we say that two programs are similar, but we should take care of that because all of obfuscation tricks are designed to bypass this similarity, and so then we propose a new approach. It's based on hypothesis that the two similar programs will choose a message in the similar way, and then we compare the relation between the in a set of message instead of the task. Here, because with the result from the code covering, we have generated different message, and they lead to different set of the program, and then we can have a equivalent relation on the chat, and then in this case we can deduce a relation on the set of message, and we call that is the input message partition, and we say that two programs are similar when they have the same input message partition. And next we can use finished state automata to approximate the input message partition. The main idea is we abstract the chat of the program with the transition state of on the automat. That is systematic work on the protocol message attraction, because we see that when the automat we can receive exactly the automat, and in this case this automat it reveals the format of the input. Here very early results, because where we see that the two programs, the wget and ping, have a same approximation. For the conclusion, the first is the smart input fuzzing, where he uses both dynamic and static analysis. We have some improvement in progress. It's in the hash case we can use the symbolic execution with the help of the SMT solver. For the second, we propose a new approach in the malware detection. And to finish, I give a brief comparison between our approach and the current approach. And thanks for your attention.
Thank you. Questions? Alexandre.
Small questions. Did you publish already the paper about this and the tool for doing it?
Not yet, because I just finished this book.
Okay, so you will publish it later. Okay, thank you.
And do you have a proof of concept or valid implementation? My question is, would it be feasible, for example, if the code was self-modifying? So would you be able to trace it in memory? If it's checking for debugger, I mean, there are a lot of assumptions in what you say. For example, it assumes you are able to trust the program. There could be countermeasures. It assumes, or maybe this is my understanding, that the message space is manageable, because if the message space is very huge, for example, if the message space includes a hash key,
yeah,
or encryption key,
yeah,
how do you deal with that?
In fact, it's quite difficult, because when we do that, we have, as you say, that we we imagine the input space is fixed because that means we have a space of input message. And what you say is when we cannot limit, for example, when we cannot limit the size of the input. In this case, we can do that because our method is for example, for this line where we use the finished state automat for the approximation. And in this case, I don't need to suppose that we have a fixed input message because why? Because you can imagine I take the same message for the two program to the two program different, and then two different program, and then when we for example when we try two different program with 100 message, and then this case we see when we see the for the fixed 100 message, the partition on this space is the same, and then in this case we have a high we can conclude that the two program in fact is the same program, but we can that means they use the same algorithm, but we can use the different code.
You got it? Yeah. Okay. Another question? 1, 2, 3. Okay. Thank you. Thank you, Tandin.